Hi everyone, welcome to the second Robotics Meetup. Unfortunately, speaker is still on the way, so I had to do an impromptu introduction. The first speaker, we have two speeches today, followed by a panel discussion. So we have some interesting discussion points on the future of robotics. But without further ado, because we got a bit late, let's start with Dr. Lanka, who is a senior lecturer at the Department of Electrical and Electronic Engineering at the University of Pennsylvania. He's going to talk to us about the presentation of industrial robotics for Sri Lanka in the Sri Lankan context. As we keep overview, his specialist areas are and interest areas are carbon-based nanostructures, nanotechnology in photovoltaics, nanoelectronics, soft actuators, body sensor networks, distributed control systems, robotics and control systems. A lot of stuff I do not know about. But I'd like to, without further ado, please welcome Dr. Lanka.
Thank you for the kind introduction. Okay, welcome to this second robotics meetup, and I thank the organizers for inviting me for this speech. I will try to focus on special topic which I had in mind for a long time. That's affordable industrial robots to Sri Lanka. Why I chosen that is I have been struggling to convince our industry for a long time the need of this kind of industrial robot. Why don't you get your robots and do some useful work? But over the time I realized certain reasons. So what I thought was I will try to simplify it as much as possible and present them so that you will realize that this is not a rocket science. This is very simple stuff, and many people can do it. So that's the message I want to give out. So with that in mind, I will start just with the definition. Why you want to call some machine a robot? This is the definition coming from the Robot Institute of America. A reprogrammable, multifunctional manipulator designed to move parts of materials, tools, or specialized devices through various programmed motions for the performance of a variety of tasks. So the essential feature for a machine to call a robot is that it should be reprogrammed. Right? So already there are robots that you make use of. For example, your washing machine. There are many modes that you can reprogram. Reprogramming is done for you. You select the modes, but if necessary, it can be reprogrammed. Now, if I go to the very fundamental, here you get here you get a typical example when you talk about robotics that people focus on the automations on the automotive industry because they need a lot of they have a lot of tasks that the human alone can't do. So whenever we say industrial robots, people refer to big factories having big machinery, doing a lot of producing a lot of things in very short time. Not only that, not only automotive industry, you get applications in commercial aspects like household vacuum cleaning, military applications, you get medical applications. This is a picture of Darwin's medical assistance system where you have robots involved in surgery. I think Dr. Gopur can talk more about these things. And then recently, about 10-15 years ago, people started working on underwater robots. We have a couple of projects going on that, and then even well before that, people started using the robots for planetary applications, space applications. Now, if you look at all these things, why people need robots is to do something that the ordinary or even the skilled people can't do for whatever the reasons. One thing is the tasks may be dangerous. So there is a health threat to the person who is going to do that. So that is one reason. Another good reason is the repeatability. Now, when a certain workman is employed on a certain task, a repetitive task, doing 24/7, it's obvious that he or she will get better. So with this scenario coming into picture, the productivity and all sorts of things regarding the quality of the output will come into the picture. So that is one other place where robotics is needed. Right. Now, when I say the things that people can't do, it goes back to very many fields. For example, if you want to deploy a person working in the mining sector, it's a very dangerous thing. And also, if the temperatures that you work with is quite high, unbearable to human beings, then again, it sets an environment where you need the service of robots. Then the repeatability and also the accuracy. So aspects like that have called for the usage of robots. Now, if I take you to the international scenario, now what I am looking at is not the y-axis. This is the money axis, but this one starting from 1995 to 2025. This source is from the Japan Robotic Association. Here you get the application of robots in various sectors. Below here is the manufacturing, then bio-industrial starting in like 2005, then the public sector applications again in the same time, then the medical in between 2000 and 2005, then home applications have drastically increased this age. Now, why the reason for this tendency is that in the society, the Japanese society, they have an aging population. So they need a lot of things that the youngsters don't have time to attend to those activities. So they deploy robots to look after their elderly parents, grandparents, and for such applications. So that is why this went on like this. Now, I am not interested in this part at the moment. What I am interested in this blue part. Now, if you take this particular country, it has been there is a rise in the usage of robots for the manufacturing industry. But if you look the average, I mean, it's been pretty constant. However, if you look at the scenario in our country, it's not. I mean, we can't find industries which are using industrial manipulators to the level that we are supposed to use. Right? So that is the motivation why I thought I will give you some hints to show that this is not rocket science, and the technology has evolved quite a lot. So what is underlying behind is simple mathematics, simple physics, and it's a matter of putting things into practice, right? So when you take the industrial robots alone, that is this state, what we get is a scenario something like this. We call industrial robots, what we mean by industrial robots is something like this, which is used in the industry for manufacturing, processing, and applications like that, mostly assembling, material handling, and things like that. And there you have basically the mechanical arm, the big body here, where you have a lot of weights associated to the body, and then you get obviously the power supply, and the task it is assigned to task, maybe a painting task, maybe a grinding task, or whatever the task is done by the end of arm tool, and this should get commands from somewhere. So that is the place where you have the robot controller, which is a computer controller, and it gets the feedback from where it is, at which angle these things are, and at which velocities they are moving, etc. Is getting from the sensors, and the programs could be installed within the controller, or it could come from the network from outside. And in addition, they need the teach pendant, or you need to teach the robot what to do. So that for that you use the teach pendant. So this kind of robots has been introduced in 1970s. And however, that technology has evolved and it's stabilized. However, we are still not using it. So we'll go through the well-established technology behind this, and I will present you a case study where a couple of undergraduates tried to make use of that theory that is taught in the class and put an industrial robot into operation. So we can make use of that case study to understand the fact that it's not rocket science, and there's the potential that, there's capability within the local community to put things into practice. So now these complex type of structure we can simplify for the purpose of analysis. If I take you to the fundamentals, you get two types of joints here. One is the revolute joint, other one is the prismatic joint. Revolute joint is you can turn it around the hinge, and prismatic joint, one part will move with respect to the other one. This is 3D view of the same. And then for this revolute joint, the joint variable, we call the whatever the variable joint variable, this is the angle, here it is the distance. And we get two types of chains. One is the open chain where you have the end of arm tool connected here, and one you get only one fixed to the ground. Then you have closed chains, which is something like this. The end of arm tool is the end here also is fixed, and the tool comes somewhere in between. So you have advantages and disadvantages of these two approaches, but these are the ones that exist. And to do the analysis, we use certain notation which is called the Danaher-Hartenberg notation, or the DH notation, where we try to assign coordinate frames to each and every joint here for the purpose of analysis. And we have the link length, the link twist, the link offset, and the joint angle, which are defined like this one. Now, in between these two, you will get the link, and at the two ends where you get the hinges, you will have you will need to align the coordinates. And now, with this coordinate assignment, we have the four parameters: this A, alpha, D, and theta. A, alpha, D, and theta. We can get these numbers here for each and every link that you have. Now, this is a very simple robot calculator having two links and two joints here. So number of joints is equal to the degrees of freedom of the manipulator. From that, what we get what is called the homogeneous transformation matrix, which allows us to analyze what is going on here, where you fix the end of arm tool with respect to the inertial reference frame or the ground, where you place your control. So anything that is happening can be translated, can be represented in terms of rotations, translations, and transform everything using this kind of a matrix to the inertial reference frame. So what we do is with the notation, we take the links and apply the notation I presented before for each and every link, and get the transformation matrices A1 and A2, just plugging in values for this cos theta, sin theta, cos alpha, sin alpha, and A and D. Now, for example, in this case, for the link 1, alpha is 0, D is 0, theta is theta 1, A is A1. So you get this. Second link, A is A2, alpha is 0, D is 0, theta is theta 2, so you get A2. So you get the homogeneous transformation matrix, which transforms the quantities here to the inertial reference frame as the product of A1 and A2. So simple mathematics. This approach can be scaled up to any higher level. I will show you a simple other example where you have 3-link cylindrical robot, where you have a rotary joint here, 2 prismatic joints there. This is an example of an industrial robot configured according to a 3-link cylindrical robot, meaning that it has 3 links and its workspace is cylindrical. That means this end of arm tool can be moved in a cylinder. So with that previous notation, you can get the links 1, 2, 3, these parameters. Similar to the previous case, you can plug in these values in the matrices A1, A2, and A3, and you get the homogeneous transformation here. Once again, I will keep on increasing the complexity. Now, this is another very common application, which is the spherical wrist. That means it's a kind of universal joint, but it's not exactly. It's kind of the joint that you get here. Yaw operation, pitch operation, and the rolling operation of these rotations meet at one single location. So this is called the spherical wrist, and most of the industrial manipulators have this one as the last joint. Apart from the first 3, it is this one you get to get something done with it. So whatever the end of arm tool, the spray gun or the grinder or whatever the tool comes at this point, right? So I'm not going to do the first 3 joints. The 4, 5, and 6 you can assign these parameters like this and obtain A4 using this, A5 using this, A6 using this. So transformation 6 with respect to 3 is this one, just getting the multiplication of the 3, right? And the beauty of this, that you can keep on adding. For example, this cylindrical robot with spherical wrist. Now the cylindrical robot, the first 3 is similar to the cylindrical robot I used earlier, and the last 3, 4, 5, and 6 is the spherical wrist here. So this is a 6 degree of freedom. You can analyze easily using this technique, and the transformation, you get 6 matrices out of this, which can be reduced to this kind of form. Now, up to this point, what I tried to discuss was express this end of arm tool with a coordinate frame fixed to the ground, right? The idea is we have to control things from the ground. to know what is going on here with respect to ground. But what it gives at the end is, given the angles or distances here, angles here, distance there, and three angles here, it will give you where it is going to be, right? However, what we are interested in is not that. We have a specific task to do. We are given, okay, you should be here, right? It has to be obtained by these joints, right? So that means you actually need the inverse of it. Given this location, you need to find these angles and this distance and this angle. That is called inverse kinematics. So inverse kinematics is to find out the angles, right, and distances, this. So basically you have 12 equations, and n, which is equal to the degrees of freedom of the manipulator or the number of joints, variables. So you have 12 equations in unknowns. So you get more than one answer, unless n is equal to 12. So inverse kinematic problem is difficult compared to the forward kinematics problem. In addition, that is just the forward and inverse kinematics. There is a certain velocity at which this n should move. Linear velocity, and you get rotational velocity. So those two are related to the joint angle time derivatives by what is called the what, right? So Jacobian consists of two parts. One is the one that is having the linear velocity, other one is the angular velocity. This is all about the theory, right? So you have forward kinematics, inverse kinematics, right, and Jacobian and inverse Jacobian, right? But let's see how this can be used to get something done, right? For that, I took a very simple example where some of our undergraduates wanted to design a controller for a data of this nature. To be frank with you, what really happened was, we got the manipulator, which is a piece of iron with some motors connected to it and some encoders, right? It's not that expensive. You can buy even in Panchika, or you can buy it. Some companies, they throw away these things after some years of operation. So they wanted to build a controller for this, and also the interface. Now, actually, if you look at the reality, manipulator is not that expensive, and manipulators are repairable as long as you have all the links, or you have the arms in place. And if there's anything missing, these things, because they use the encoders and they use AC servo motors, maximum they will have permanent magnet AC motors. Still, it is handled. I mean, you can handle it. There's no big deal about it. So the thing is, in order to build a controller for this one, forward kinematics is fine because you can get the measurements. Inverse kinematics is just the inverse. It's a geometric problem, trigonometric problem. And then for the Jacobian, again, you need some more information. And when you design the controller, you need to know about the masses, the inertias, and things like that. Now, what I'm going to is how we can do these things in a very simple, scalable manner. So what we did was, basically we modeled this whole thing using a CAD tool, we prepared this one and inserted the material and material properties, and then we could run the simulation model of it, and right. So this, the one that I showed was a SolidWorks model. So thereafter, what we did was we tried to model this thing using tool in the Simuli, where we have the various joints connected via the links. So what we have is for the robot model, torque is the input and the angles are the outputs. However, this comes for the actuator for the manipulator is a motor, so you need to add the motor. At the motor, input to the motor is a voltage, so it gets extended like this. And the simplest form of control that one can have for this kind of a manipulator is to have independent joint control. That means the joints are considered as the plant, and you disregard the rest of the things that are connected, disturbance, and just do a simple PID control or whatever the control that you can have. So this is the very simple type of control, but you come across problems because consider the others as complete disturbances. And if you buy out there in the market, this is what they do. Right? So we started with that. So from our theory, what we get from the forward kinematics is, given these angles, you will get the positions in X, Y, Z, and the angles you pitch and roll. This position kinematic relationships, desired X, Y, Z positions, you pitch roll angles, you will get theta 1 to 5. Right? From the forward velocity kinematics, you use the Jacobian, theta 1 dot to theta 5 dot, x dot, y dot, z dot, and the time derivatives of the angles and inverse kinematics. You have the desired values and you will get the required angles. So you take this closed loop system with independent joint control and do the same thing. You get the desired position. In using inverse kinematics, derive this one, apply that as the reference angle here. Use the forward kinematics to obtain this one and compare this. Very simple feedback control, and this is what you get as the typical outputs that you get for step inputs. You could see that you have these things. One could argue, why don't you PIDs? It will do. But we made an assumption that except the joint concerned, everything else is a disturbance. So that is not going to work all the time. So that is the catch where you get unwanted stuff like this. So it is hard to control. The tuning is task specific, so you need to consider the arm dynamics into this. So now I will show you quickly how the dynamics can be taken into account and come up with a better control. Here, a little bit more details, more equations, so don't worry. All what I have expressed is the kinetic energy of this manipulator. manipulator, and I defined the Lagrangian as the difference between the kinetic energy and the potential energy, and use the Euler Lagrangian formulation to obtain the torque equation of the robot manipulator. I get the dynamic model of the robot and displays many of the parameters that you get in the dynamic matrix, the gravity matrix, and the matrix here. You get a lot of parameters which you need to get from the reverse engineering task that we did by modeling in the software. So, from the SolidWorks model, you can get many of the parameters which are required here. Parameters you can obtain from there. So, by that, many of the parameters needed, you don't need to refer to the manufacturer data sheet. Without that, with this, we could add. And then, when we put this dynamic model here in place, again, the input is torque input and the outputs are the respective joint variables. Next, we have to keep in mind that even though this is the generic model of the robot, by the motor. So the torque comes from the motor, so therefore it has to be some voltage at the input. So we need to incorporate the DC motor also into the. So the motor dynamics are added, and this is converted to voltage. Input is voltage, and output is the respective angles. And this equation with U having the units of the torque can be expressed like this. And this is the full model of the robot. With this robot, we go and do a dynamic control design. So the plant is this equation, which is exactly the same as this one. And I take the controller, everything equal to this except this double dot is equal to exactly the same coefficients except this one, and I define this Q double dot should be equal to this. And I choose AQ as a PD control reference, and the reference consisting of Q reference, Q dot reference, and Q double dot reference. You can insert joint variable itself, joint variable time derivative, and the joint variable second time derivative. And the beauty of this approach is you can define the tracking error as the difference between the desired value and the actual value, and tune the dynamics using the dynamic equation, where K1 and K naught are gains, diagonal matrices in the natural frequencies of oscillations as the coefficients. Right? You can independently control the dynamics of each and every joint. So you decouple the problem into a multi-input, multi-output type of system. So the implementation, when it comes to the implementation, the desired values of the generated by the trajectory planner, this gives what task the robot has to do. And then you have the outer loop generating the AQ using these values, and the theta is coming, which is input to the inner loop, which gives the torque to the robot respective joints. So basically, since we are using the inverse dynamics, this is a nonlinear controller. However, it beautifully allows us to handle the dynamics of the manipulator. So we have the inverse dynamics control in place, which gives us the respective voltage for the respective axis, and where the inputs are the references from the trajectory generator and the outputs are the angles of the respective axis. And this is how the simulation results look like. Designed to do critical damping, and in the simulation it works quite well. So what we did next was to replace this mathematical model of the robot dynamics with the SolidWorks and ask the computer to simulate exactly the same model that was used to obtain. So this is a kind of verification. You just replace this with the SolidWorks model, and this is how the results look like. So this is more or less the same. So, and here we did a little bit of comparison. The reference, and the black one is the dynamic controller, and the green one is the independent joint control PID. And is the real one which we wanted to do, that is the hardware. So you basically replace the SolidWorks model of the robot with the actual. So you replace that here. In addition, you will get two interfacing material in between and the dynamic controller on the electronics, right? So the whole point is this goes some additional interfacing material, and this is replaced with the actual machine. And you could these are some of the results of this implementation. And here again, this is the actual result of the independent joint control versus dynamic control. Here, this in place. So very simple crude, and this is the interfacing software. So basically, the steps that we followed, basically we started with the mechanics model, and then derived the forward and inverse kinematics. Started with the simple PID type of independent joint control, derived the complete mathematical model of the robot controller, and verified the operation of the derived controller in simulation, and verified the accuracy of the mathematical model of the robot, and verified the operation of the derived controller in hardware domain. And so this basically established a procedure to develop an inverse dynamic for whatever the controller for industrial manipulators, where we don't have the details. We don't need the details, right? So you start with the manipulator itself, reverse engineer the content, and use your theoretical knowledge in practice. If you want to buy this particular hardware, I mean, if you say you want to import it, it will cost you like $2,000. But in this case, it didn't cost us 20,000 rupees. So that's the difference. And most importantly, one would ask whether this is scalable. Yes. Scale manipulators are 6 degrees of freedom or less. The one which we handled is 5 degrees of freedom, and you can scale it up or down. So with that, conclude. I took a few minutes extra, and thank you very much for listening. Have questions during the discussion.
I think we can start question now. Okay, just immediately on the topic.
Any questions?
What's the time span for the whole session?
3 months.
3 months. How many people just keep the which level finally?
Final year percent.
Somebody to make master in subject of robotics. So to come up to the level of designing a robot and as well as a controller unit. And abilities he person should may have skills. I would like.
Good knowledge of mathematics, physics, electronics, and hands-on.
You asked about like we need to model our robot in SolidWorks, right? When we are modeling the robot,
That is one way of doing it.
yeah, yes. When we are modeling the robot, we need to know exact details. That means the exact dimensions of the robot, or else the dynamics will not be the same with the thing. So how do you get that details? Like if it,
In this case, we have the manipulator in hand. We can measure.
using, you say maybe a money calculator or something like that.
You don't need to disassemble because you take the measurements, feed it to the SolidWorks model. Then when you insert the material types, calculator using that.
Again, selecting the material will be a tough task. Right?
Yeah,
don't know how
you should
to
know the
material.
material.
Yeah.
But the components are either aluminium or steel, stainless steel, and things like that. So it's not very strange material.
There can be aluminium grade.
Yeah, that's why we do verification actually.
Yes.
It should match the experimental results. Yeah, I agree with your point.
Measurements is like if you are using a 3D scanner or something like that, that may work, but using some sort of way measurement, well, dynamics can change with a smaller change in the design, or maybe nut and bolt can change the dynamics.
Yeah.
Well, actually, the beauty of the PID control is it's robust. It takes care of this. So you really don't have to worry about exact parameters as long as it is within the ballpark values.
Any other question?
I think we have a mixed crowd here, right? So there will be people who easy to work with, and there will be people who are very interested to really start up and try something. And that's industrial robotics. But is there any recommendations of technology stacks or things like Cylon.js or different kits that you would recommend for enthusiasts to really get started, start playing with robotics or anything like that?
To be honest, I didn't recommend the kits. I gave them the motors separately, encoders separately, the electronics separately. I asked them to. I think if you go to Robot Shop or something, the website, you can order stuff. And also, I think there's a site in Sri Lanka, Lanka Electronics. They also have some kits. I mean, I won't recommend the kits simply because one should know what is going on by him or herself. Having the theory in mind. Yes.
Dr. Samanayak for that educational talk. We'll move on to the next presentation, which is about assistive robotics from Dr. Rohan Konapura. He is a senior lecturer at the Department at the University of Mortua, and his topic is assistive robotics. I think it's very interesting that today we have on one side we have the interest about robots doing the job of humans, and you have I think assistive robots, which is about enhancing humans in a way. So we will have some discussion on that topic. So Dr. Wan is also sorry, research interests are in the area of assistive robotics, rehabilitation, and medical robotics, and biomedical engineering. Those are questions you want to ask after his session. Over to you, Dr. Wan.
So thank you, Chamendra, for the nice introduction. So I'll have a lot of videos. That's why it takes time to. So, first, if you can remember, first robotic meetup we discussed about UAVs. Professor Rohan Musinga, president of RS Robotic and Automation Society, he discussed about the UAVs, and then we had IoT presentation, and today we had from Dr. Leland industrial robots. He showed a curve. One part is not interested, but I am interested for that part. So I am going to present about that part, that is assistive robotic devices. Robotic devices. Today I have selected robotic prosthetic and devices. If you mention assistive robotic devices, of course, all the robots are assisting the human being. But what is assistive robotic device? To show you the difference, I will show you some videos. So probably you have watched these videos, and but I want to put all of you in one platform. That's but some of I have not given the permission, and but I'm sure they are not going to sue with me because I have taken this for educational purposes only. Right. So this is a Dragon Runner, a field kind of robot, combat robot used in the urban combat. Right? Probably have watched videos. It is a rugged robot, can withstand for any kind of impacts. You can see, and very high speed, a field robot. So you can see the power of that robot. That is a field robot working in the field. You have probably watched this one, which is a famous one, Big Dog, Boston Dynamics, Big Dog, which is a biomimic, mimic the biological creature, the dog. Right? It can move in different terrains, tough terrains, in the slope, and you can see how it can get balancing as a dog. These days, there are some ethical issues to keep this kind of robot like this. Even if it's a robot, whether it's good to kick like that, like a dog. So that is a big dog, biomimetic. Of course, Dr. Leland had a nice presentation on industrial robots and short and sweet presentation which required theoretical background. Watch and what I'm going to. This is bionic prosthetic hand now in the market. So you can see it can get several grasping patterns. So he has to change the thumb motion to get the pinch grasping. And this is another robot prosthetic device we have developed a few years back, 3 years I think. So you can see the device. Of course, we can understand it's bulky, but this is the initial phase. Transtrivial robotic devices. Transtrivial means amputation is below the knee, right? So you watch some videos in there, robots. Still, these are also robots. Important differences in those videos. So if you can identify what is the difference. Anyone? Now, since we want to go forward, in here, industrial robot, can you see any man there? No. But in here, everything is attached to man. So therefore, in these cases, assistive robots, the safety is very important. Safety is paramount, right? Therefore, unlike in industrial robot, we have to take care of people because the person is in the loop. So therefore, the prosthetic devices, we have to consider the safety. Kind of again, orthotic device. Orthotic device. I'll explain you what is an orthotic device later. So this is an exoskeleton. Again, I'll explain what is an exoskeleton later. This is the exoskeleton is using for the limb rehabilitation. So what the therapist has to do is teach the robot the motion, then robot perform the motion. This is upper limb exoskeleton. This is again HAL, famous hybrid assistive limb, developed in Japan, Professor Sankai. Right. Understanding, we will move forward. And today I'm going to present this thing, background of these prosthetic and orthotic limbs, and more detail about prosthetic device and robotic orthotic device. Control it. What are the things we can do in this area in Sri Lanka and what we have done. So if I put this device in a kind of a categorization, so we can have biomedical systems, and biorobotic is one part. The robot, but biological creature is involved. in these cases, we are considering human as a biological creature. We have other few categories: assistive robots, medical robots, and other types. So the things which I am going to present today is under assistive robots, prosthetic devices, and orthotic devices. Again, those prosthetic devices or the prosthesis or orthosis, we can categorize in several other ways. So why we need these kind of devices? As Dr. Leland correctly mentioned, now the society is age society. That means more percent is about 65 years age. When it's come to 220s, percentage is increasing. 2050, more than one third is physically weak because of aging society. So there are with different label or disability, and number of people because of the age society need help to do their day-to-day activities to make them more productive to the society. So therefore, technology can play a major role. And in that case also, robotic technology major role. So that's why we are going to develop these kind of assistive devices, robotic processors, and orthosis. Prosthetic device. What is a prosthetic device? It is an artificial device that replaces the missing body part. It can be missed because of several reasons. In the Sri Lankan context, because of the congenital disorders or accidents, diseases like cancers or diabetics, body parts can be amputated. And also, as for casualty, there are amputations. So a lot of people are now, considerable people are with amputation. For them, if you can replace the missing body part from a device, those devices we can hold as prosthetic devices. You can see the body part here, the amputation is transhumeral. Between the shoulder and the elbow, we call it as transhumeral amputation. If the amputation is between the elbow and the wrist, we call the amputation is transradial. So this is amputation is transhumeral. You can have this kind of artificial device, which we call a prosthetic device. Then with that, people can do upper limb, which we call upper limb prosthesis, upper limb, lower limb, and other types. Other types, we have prostheses for each and every body parts, like ear and for nose, like if your body part is removed, prosthesis. But here I'm going to focus on prosthetic limbs. So again, based on the actuation, also we can categorize prosthetic devices. Or cosmesis. We call cosmesis. Cosmesis is just to give the appearance. It cannot perform any functional tasks, just to give the appearance. You can have cosmetic prosthetic device. And body-powered prosthetic device. Now, even though your part of the body is amputated, some other parts can give the power required for the prosthetic. So we discuss these things detailed later. And then external power prosthetic. Those are the robotic prosthetic devices. So we are mainly focusing this part today. So this is a cosmesis, lower limb cosmesis, prosthetic device. And this is a nice lady. And this is the prosthetic device. Right? So this snaps. The prosthetic is not there, or it's kind of odd, right? So at least cosmetic prosthesis is needed, these kind of people. And this is again a prosthesis. Likewise, these are cosmetic prosthetic devices because cosmesis only outer appearance. And this is a body powered device where amputation is in this place that we call the transradial amputation. And but still these parts, stump arm from shoulder to elbow is available. In that case, if you can use the power of this part, we can actuate the hook. So then cup, you can beat the cup and perform task, required task. So this is the arrangement, and you can see this cable. Wearer does the motions of the shoulder. This cable extends and hook open, and then he can get the cup. So this is how body part processing works. So he can wear the prosthetic device. This is the device. So this way he can wear the robot very easily. And then when he does the hook opens and he can grab. You can see how the person can open the hook. From this one, he can do some day-to-day activities. It is hooked also. Right. So then we will discuss about robotic prosthetic device. Those are cosmetic devices and body powered prosthetic devices. So unlike in body powered or the cosmetic prosthetic devices, so this robotic prosthetic device, they can assist for the daily activities, the amputee. Of course, if we design correctly, the robot can act as a cosmetic device. Famous robotic prosthetic devices. So this is a iLimb. It is in the market. So with the prosthetic, he can perform some of the activities. And this is another such kind of device in the market, is still in the clinical trials, DECA arm or the loop arm. So US Defense Agency initiated this project initially. So unlike in iLimb, this is a modular one. That means you can separately get the modules for the hand, radial processes, modules for the transhumeral processes. So with these devices, they can perform their at least day-to-day activities. This is again the DECAM, LUCAM, modular based one. And these are the commercially available prosthetic device. DECAM, outdoor box sensor hand, Boston elbow. So this is a terminal device which can be attached some other prosthetic devices like Boston elbow. You can attach this photo book sensor hand. Only the hand part is available. Right. So then we move on to the orthotic device. Again, another kind of assistive robot. So the orthotic device. Now, in the prosthetic device, your body part is normal. It is amputated. But in orthotic device, your body part is there. But the problem is it's weak or it needs support. So orthotic device are to assist, support, or strengthening, or to improve the function of body part. The part is there. The orthotic devices we can categorize in several ways based on the location of application. Upper limb, lower limb. So these are orthotic devices for upper limb and lower limb. So these are not robotic orthotic devices, just to give some strength, not a upper limb, lower limb, and other type of orthotic device. This is to support the lower back. So the robotic orthotic device in upper limb, lower limb, or other type, and also we can have other categorizations also. So this is this is exoskeleton robot. Exoskeleton means where your inner skeleton is there, right? But outside the body, you will have another kind of structure, mechanical structure, and joints corresponding to the human limbs and joints. So this kind of robot we are defining as exoskeleton. Exo means outside, skeleton, kind of skeleton. This is a famous such kind of device, and this is lower limb exoskeleton. Again, this is lower limb, and this is again a exoskeleton device. So these are few famous exoskeleton robots. This use as actuators DC motors, and this one pneumatic fluid muscles. These are the muscles used for the actuation. Some kind of prosthetic device, exoskeleton robots. This is arming robot, which can now when we do the upper limb motion, the center of rotation will move up and down. To cater that one, this robot is developed. HAL, famous hybrid assistive limb, developed in Japan, Tsukuba University, Professor Sankai. So this one is in the market. This is a full body suit. They are renting full body suit or lower body part, or if you need upper body part, they are separate. Then let's see what are the application of these exoskeleton robot. Of course, they can assist, power assist. If you are physically weak, if you don't have required power for the day-to-day activities, these devices can give power to move your hands. That means you don't have required power, so they can elevate your power up to the required level, or else they can augment your power. That means you have the required power, but you need more power. Like in military applications, if you want to carry backpacks, we can use these kind of devices. and also for the robotic rehabilitation, limb rehabilitation, and also for the teleoperation. So we will see, we launch videos related to each and every application of this device. This is actually the robot in Saga University. I have done my PhD with this kind of structure. So this is the exoskeleton robot for use for the power assist. Human power augmentation. So we'll see Berkeley Bannon. So you can see that he can carry the attack with the use of this exoskeleton robot. So with the exoskeleton, user does not feel about the extra weight. So this kind of exoskeleton you can use if you need more power. So this is the application of exoskeleton robot for rehabilitation, especially limb rehabilitation. Initially, the therapist teach the motion. The motion pattern is required. This can be taken from the expertise of the therapist from the motion. And then this is teleoperation with the robotic exoskeleton. So you can see the exoskeleton device. So the model is operated, input taken from the robot. Right. So then we'll move on to controlling of these devices, prosthetic and orthotic devices. So these devices are part of actually after wear it, then these are part of the human body. Then they should work according to the motion intention of the human. Otherwise, those are useless. So therefore, to control these devices, we have to extract human motion intention. So that is part of these kind of projects. But for to get the human motion intention can be used. EMG, electromyography, muscle activity levels, or EEG, brain activity. Sensors they use. You can use EMG and EEG or biosignal plus external sensors. And other methods are available. Those can be programmed. Like if you can use if you want to use a lower limb exoskeleton device, we know the working patterns, but which we call the gait patterns. So we can program the robot to generate gait patterns. But in those cases, there are again other issues are there. So then, how to control these kind of device using biological signal? We say we will take EMG, which is electromyography, the muscle signal. Now, if you want to say if you want to do a motion, so initially what will happen is in the brain, motion intention is generated. So the intention passes through the nerves to the required muscle. Say I want to do the elbow flexion and extension. Initially, the brain motion intention generated, the signal passes through the muscle in here, biceps and triceps. Then those signal from the nerves, it passes to the muscle, electrical signal. Those electrical signal then converted to the mechanical power. That is the process. So from the electrical signal, when it's converted to the muscle power, there is a time delay, 200 milliseconds. So if you can extract electrical signal and process them and use to control the robot within that period, so we can go, human and robot can go together, right? So this kind of device, muscle signals are used. But in prosthetics, limbs are amputated. In that case, we don't have a way to extract muscle signal, because muscles are no more. So in that case, we have to think a different way. Now this is a EMG based control of prosthetic device. But to control prosthetic device, if you use EMG, you need a muscle. But in this case, the limb is amputated. But end of the amputated part, nerve is there. From that nerve, we can attach the nerve surgically in a separate muscle. That we call targeted muscle reinnervation. So that in that case, so if you attach this nerve to another muscle, so when the person thinks I want to do this motion, the muscle in here activates. Then from that muscle we can get the EMG signal. Using those signals, we can control the prosthetic device. So this is 11 years back prosthetic device. So you can see now he is thinking he wants to do this kind of motion. He is thinking. Then muscles in here activate. Muscles. Normally, surgeons are using chest muscles because using chest muscles, you are not performing other kind of motions. To reinnervation, what they are doing is available muscles are removed, available nerves are removed, and the nerve ending in the amputated body part is attached to the chest muscle. So this is 11 years back. Now the technology and devices are more sophisticated than this. So this is the TMR, targeted muscle reinnervation process. Body part is not available, but signal is there. So then attach the nerves to the chest muscle. So then when he thinks I want to do this motion, but for that I think there are training is required. From that muscles you can control the device. That we call targeted muscle reinnervation. Right. So then this is the control of this is the loop arm, which can be controlled signal of foot pattern. So you can give the input from the foot pressure sensor. So in these ways, we can control prosthetic and orthotic devices. Right. So up now we watch some videos of foreign institutions. We will look at some videos related to this area in local institute in our laboratory, bionics laboratory. So this is actually 4 years back development of robotic low limb exoskeleton device. This is in 2011. So you can see the motors. We use Viper motors, but we failed. Right. only we could develop the structure and backpack, but we couldn't, even though the person is performing the motion, it is not assisting because this motor, vibro motor, needs 24 amperes. It's difficult to control with the motor drivers. So we try to develop the motor drivers, it's again failed. So this is a good example, but we failed. We learned from a lot of things from this. That is in 2011. So then we developed prosthetic device. Again, previous one is exoskeleton. This is a prosthetic device which I have again shown earlier also. So we controlled it using muscle signal. This is a controlling. Try to mirror the motion. This is the controlling of this device from muscle signal. Still, devices are bulky, and we need more sophisticated control systems. And then we developed again another mechanism to adaptation. The mechanism can adapt based on the object which is trying to bring. So it can generate 4 grasping patterns. Still, this we cannot use for with the amputation. Still in the research state, we have to do a lot of improvements. But for the mechanism, we have applied Sri Lankan paving. And this is again another mechanism. Previous one used linkage. This one is stable dual mechanism. Now you can see the difference with linkage structures. Now 3D printed. That means we are getting more funds. So motors are Maxon motors. Again, this one can get the adaptation and some few grasping patterns. And now the last year undergraduate student developed this one. So now we are getting more and more funds. So they actually use the EMG signal to control the device, but 2 signals they have used. So developers are in here in the audience. If you have any question, you can ask. So bicep muscles we are using to control the different motions. Muscle the motion shifting. We are using isometric contraction of the muscle. Still, this cannot use as one unit. Circuit is in the different place. You can see the wires and you can see the gears and everything. We have to replace those with tiny gears, and also we should have covers and a lot of work to be done. Right. And this is not a prosthetic device and orthotic device, but I thought it's important to show this one also. This is a male assistant robot developed in the Bionics laboratory. Actually, principal investigator is Dr. Deenalaya. So EEG signals are using to control this meal assistant robot. You can see three basket of foods. So you can see the LED panels. From that visual stimulation is given to the brain. From the stimulation EEG signal is generated. Those signals is used to control this device. And then from the spoon we carry food from the near to the mouth, and then they identify the mouth, and after the mouth opens happen, the robot eat the food. The developer is in the audience again, right? So those are the devices we developed in the University of Morocco Binary Laboratory. So still, if you want to attach those devices to the robot, to the human being, we have to do a lot of research. Probably this is output of 5 years. After 5 years, with a lot of hard works, especially for, in the funding. So we have to do a lot of research, and we can at least have a basic type of device to be attached to prosthetic amputees within probably 5 years, I say. So these devices, the research are still going on in different places in the world. But then we'll see what is the future. Now these devices are control methods are there, few robots are available in the market, but still need improvements in especially to identify the human motion intention. And also now people are trying to, now these devices assist the motion or sometimes power, and people are trying to kind of overall assistant where they can not only assist power, assist perception. That means for the vision assistant, they can use a kind of camera. And also these devices should be developed as kind of a second skin. If you consider exoskeleton device, you can see it's still bulky in the world level also. Researchers are trying to develop like a second skin. And also people are thinking that in these devices, if you can help the human being, these devices can carry a lot of other things. Like if your mobile phone is inbuilt in the device, and music player, everything is inbuilt in the device, and then you can use those devices with those equipment with the device. And for that, you need a lot of power. Those power they are trying to get from the motion, human motion. So this is the now status of these prosthetic and orthopedic limbs, and thank you. We have Q&A or
Yeah, we have some questions. Do you have any questions right now, Dr. Ron?
Are there any platforms like open source or something like we can start building those type of robots, or do we need to start from scratch if we want to build one?
Yeah, for the moment, actually, I think there are no kind of platform, right? So as we need, we have to develop from the scratch. Because then this is different type, not the industrial robot, not field robot. It should be attached to the human being.
So, are there any research based on developing a platform so that anyone can customize it? Because those amputations, they are not actually, it is random, and you can't say from where you can't. There is no standard to develop, so it should be customized for each robot.
Yes.
So, if there is a platform there anyone can take it and they can improve it, no?
Yeah, yes, yeah.
So are there any research
Yes,
related to that?
we didn't come up with such kind of devices, platforms. I think I'm correct. My team members are there because they are searching every day. I think we can't find the platforms.
Small, uh, a small, I can't remember the name, small CPU where you can customize and make small things.
Is it a prosthetic device or?
No, not something like that.
Yeah, yeah.
You can make a small robot using that CPU and connecting some other.
Are you mentioning about Lego platforms? Yeah, okay.
That kind of thing can be used as a small.
Are you mentioning about the mechanical structure or the control and hardware?
Only the on the CPU actually.
Right, right.
So I think he was asking something where you can assist learning things like these to start with something. So I think Raspberry is something where we can do something. I mean.
Yeah, that the general purpose robotics you can use, but these kind of devices, the structure, mechanical structure is the. So, just me. Last meetup, one gentleman asked me, is there a place to buy these kind of prosthetic? Probably, yeah. Now there are places to buy these kind of prosthetic devices. 4 or 5 companies, but they are importing the device, and the problem is whether it is suitable for the body sizes of Sri Lanka. Right? And if you are growing, if the attachment is not sufficient, then there will be a problem. Such kind of problem was there for one low college student. Her hand is amputated from, I think, transradial. Then she's limbs are growing, so then there will be a problem. Then if you import from other place, then how to do after sales? That kind of problems are there.
There is a robot,
Yes.
Which assists the let's say old people or the patients to rehabilitate the patients. It's like a physiotherapist, a robot that will sort of help hold you and help to move your limbs and sort of somehow rehabilitate the person.
Yes.
How to which category does that particular robot belongs to?
Oh, what do you mean by category?
There was some.
There is an orthotic device.
Yes.
Orthotic
That's right.
Yeah,
Yes.
exoskeleton devices.
Yeah.
Okay.
Interface for developing that type of robots in the slide number 27.
Yeah, that is the meal assistant robot.
Yes.
Actually, so they have developed the brain computer interface to control this robot.
Yes.
Yeah. What is your question?
Can we use brain?
Yes, yeah, of course, yeah.
Can we use the IoT technology with this with the robot so that we can control our body with the help of machine?
I'm not clear what you're asking.
No, let's say it's like this. We are a person who is who has been undergone treatment for something, and
is on prosthetic limbs as well as artificial, let's say, any medical device, externally to function, to make the body to function as now as it is.
Yeah, then now the
So,
yeah.
so whenever that has to operate, can we? Is there a possibility of making that to operate through these devices? Let's say wireless devices or whatever.
So you're asking about the surgical robot?
Yeah.
The surgical kind of surgery support system and surgical robots are there. Master slave systems. Dr. Lilantha showed one slide. So the robots can be used to you can be used for surgeries. Master is in one slide. The surgeon is the master robot. Using the master's motions, the robot can perform the motion near the patient. That kind of devices are there. One is the Da Vinci robot.
It's not a surgical robot.
Yeah.
Now let's say you have undergone a surgery,
Right.
and or accident, whatever, and you lost your limbs.
Right.
Now you are with the prosthetic limbs or arms or whatever.
Right.
Some external devices
Right.
attached to your body.
Right.
So to make that function properly, can't we use a radio signal to this limb or whatever, limb or yes, I'll say.
Right. You mean you will use external signal to control the device?
That's right. Yes.
Yes, we can use.
So okay.
Okay, thank you, Dr. Ron, for that very educational talk. I'm very interested in bionics, actually. I don't know, I don't think any of you remember, there was a program in the 1970s called the Bionic Man, the $6 billion man. And it was all about a man who had been an astronaut with a major accident, but in the process of, he lost his limbs, he lost his hand, he lost his eye, and the process of actually building up, it took $6 million, which is a lot of money at the time. In doing that, they made him a superhuman, right? So he could run about 60 miles an hour. He could, with his eyes, he could see, fantastic distance. With his ear, he could hear great, and hear in a range that only maybe animals could hear. So we're going to have an interesting discussion now with the panel, where we're going to talk about these two things, right? Where we have robots which are going to, do more and more of humans' work, and then we have things like bionics and assistive robots which are looking at enhancing humans to a certain extent. And we will talk about the evolution of these two concepts. So I'd like to first invite two speakers, Dr. Ruan and Tulianta, to take a seat, please. I'll introduce the other two. Thank you, gentlemen, for your presentation. The other two speakers is Dr. Mike Palak. Please join us, take your seat. He's a senior lecturer at the Department of Mechanical Engineering from the University of Virginia, and his research interests are modeling of nanoscale electronics, thermal transport, geometric methods, and he's particularly very interested in mobile robotics and computer vision and pod robotics, so you can ask him questions in that area. I also like to invite Dr. Luanta Viseram, our main industrialist from actually Nikimi Automation. He is been with University of Mortar since 2002. graduated with honors, and he's a director on the board of Nikki Automation. Who's really going to talk to us about how industrial robotics is being applied today in Sri Lanka. And since there's nobody else to introduce me, I'll just introduce myself. I'm Chamindra De Silva, which I'm from. I work at Virtual Polaris in R&D. I work right now in the area of cognitive computing, chatbots, conversational bots, and robotic process automation. So that is work more with regard to IT automation, and we're doing a lot of work in that area. Okay, so I have a series of questions, and there are three themes. The first theme is I really want to find out what are the unique opportunities in the industry in terms of industrial robotics and assisted robotics. What ideas we have from the panel. The second is I really would like to understand the dynamic between assistive robots and industrial robotics. Is there a advantage that assisted robots can create for humans in the workplace? And then I'd like to talk about the future, extrapolating to the future. Given everything that's happening in the world today, what are we looking forward to? Is it doom and gloom, or is it a positive future? We have lots of science by-side stories telling us about things, what will happen if AIs take over. So it's I think an interesting topic to just think about as well. Okay, so I have questions for each one. I think we're going to be late. I'm going to skip through the first lot. So let's start with the current status quo in the industry. I'd like to have a question to Dr. Vanta. A little bit about the present state of the application of robotics in industry and how it's progressing.
I think coming on to Sri Lanka situation, I can share with you about 30 years back. Our company started as an automation company in Sri Lanka. So I had the privilege to join 15 years back. On that 30 years back, when we talk about automation to industry, so nobody was willing to listen to it. There was ample amount of labor available, and people were not bothered going for automation or going for robotics. But with the time, it has changed. Situation today is, for industries, it's very difficult to find people. Now I can share with you, if you publish a newspaper advertisement asking for some skilled labor, hardly you get any CVs. Today, willing to do repetitive work. They are not willing to do tedious jobs. So they are very selective in selecting the particular job that they want to do. So in that sense, now we see a huge demand in automation. I think this Dr. Ruan and Dr. Niranta, they have done extensive work on this one. I think now in Sri Lanka, what we have to find is how to apply these things to the industry. So I see there is some sort of a gap that somehow we have to find ways to bridge. Situation, I think there's an increasing trend for this application of robots and automation in Sri Lanka.
We just asked where is it being applied today?
Basically, now when we look at it, mainly we see in industry for material handling, there is huge demand for this automation. So I have seen some companies, they are using robots, but not developed in Sri Lanka, they are imported stuff. I could remember we have developed some time back vehicle. Now instead of using a conventional conveyor to move items from one place to another place, vehicle. So that still, I think still we are struggling to find the right industry to push it. But I'm sure time will come where people will get those stuff.
Thank you. Sorry. You talked about automated vehicles. I'm going to ask the next question from Dr. Sanjeeva, who is specializing in mobile robotics. What is the latest state of the art? And is there opportunity in Sri Lanka? I don't know about the road conditions, but can something like Google and the cars be driven in Sri Lanka?
Well, I think before we go to self-driving cars on the roads, like Ranta said, I think the industry is long way from adopting material handling mobile robots. So I have always felt that there's a promise in that area. And my expertise is in the field of mobile robots, auto-guided vehicles, including aerial vehicles and mobile robots. And there are significant challenges theoretically on one side and practically implementing them technically on the other side. And thirdly, from an industrial perspective, like Ranta said, where people are still reluctant to accept it. But there is tremendous scope. People are using this everywhere else in the world, whereas we are not very open-hearted towards this. So in that sense, there is a bit of a problem. But so if I say talk about from the theoretical point of view, it is still an unsolved business about how to control and navigate a mobile robot. Let's say a ground robot. If you talk about a ground robot, it's a mechanical device on the first hand. But then how do you get it to move? That is actuation. Then you require electromagnetics and electronics. And how do you convert this electrical power stored in a battery or something into the mechanical power moving the device? So that makes it an electromechanical device. But then this device is handicapped in the sense, like Dr. Yolanda was talking about fully actuated joints. But this is an underactuated joint system because you don't have freedom. You cannot actuate all the degrees of freedom like aircraft. The aircraft cannot move unless it is moving forward. So if you want to navigate, you have to move forward. So while doing that, how do you make sure that it goes from one place to another following a desired trajectory? So these are challenging theoretical tasks which our people still are thinking about. So from a Sri Lankan point of view, we can try to address these things. Why? Because these only require your brains, theoretical knowledge, and to verify them, you can use a computer simulation to try them out. So there is a lot of scope in that area. That is one. Next, when you try to implement them, then that's a totally different business, as you have seen from the efforts that Dr. Yolanda and Ruan have been doing. They have made great progress. And but when you try to do that, there's a whole lot of different stuff. But I believe maybe others have done it. But we have to start doing it from scratch, like they have to start doing it, because we have to develop this capability in-house. We cannot borrow things. We cannot start depending on others. If we start borrowing things, if we start just implementing things what others have done, we will every day depend on them. We will never be able to catch up to the global trends, and we will always be missing the bus, as everybody says. So we have to start doing it from scratch, like what they have been doing. They are doing it from scratch, and someday, hopefully, they will catch up to the global trends. Because so I think we have that capability, and so there's a lot of scope if all those three things fall into place.
Thank you. So I think I take your point. I think certainly if we get those parts from abroad, they're very expensive, right? And it's hard for us to create a competitive advantage. So I think we have to build components from scratch. How, if I could ask Dr. Lilanthan, how do we create this ecosystem in Sri Lanka?
Well, creating the ecosystem has to start at the school level, I guess. There has to be some motivation for one to get engaged in this kind of activities. For that, I think, first of all, if you look at the history, there should be some social reasons to get engaged into this one. I think I mentioned in the, and Dr. One also mentioned the same thing. Japanese people have a social problem for them to get engaged in robotics, aging population. And also after the World War II, there were a lot of victims with disabilities too. So that was a national problem for them. So they found robotics to be a solution. Likewise, for us, I see that we have a couple of things. The young generation move towards tech-savvy jobs. So our agriculture is finding difficulties to have people. So that's one area that if you expedite on, you can put robots there and get maximum use of it. Likewise, we have to keep keep the grip on the society and then start thinking how we can how we can use this technology to the betterment of the society. If you don't try with such a link or such a relationship, then it won't sustain. Then it will. I mean, people will do just for their interest, and then it won't last long. If I take another example, there are repetitive jobs, whether they like or not. I mean, especially if I take the garment industry. I don't know whether there are representatives from the garment industry here in the audience, but to my knowledge, they have realized this. Workers getting fatigue while they do this repetitive job is getting into their scenario now. So they are a little bit moving into robotics, but not to a great extent, but they are looking for. So likewise, we have to have a realistic reason for us to embark on this whole scenario. So, as I have been telling, it has to come from the society, and these concepts should start developing at the level of the school, then the university, then the technical colleges, and the other tertiary education systems, and then through education only we have to start doing it. Of course, on top of that, one has to have his or her own interest. Provided the interest is there, the rest has to come from the education. That's what I'm saying. And also, as a society, the rest of the society should have the mindset of accepting the local solutions. That's another thing which I see seriously lacking in Sri Lanka. That's another reason why many of the, not keep aside the robotics, but if you take other things also, why the local solutions don't sustain is another.
Thank you. So I think it's a very key point in terms of robotics. It's I think a lot of the focus, I think the cultural focus should be to focus on the jobs that people do not want to do, or there's a dearth of skills or people doing that, like the agricultural sector. And I think also elderly care, also in Sri Lanka, do you think? Elderly care, I think, also would be a focus area, wouldn't it?
Yeah. Yes. Previous panel members has correctly said there is a gap in the Sri Lankan industry.
Yeah.
And also, Dr. Sanjay mentioned we have to build our own things. When we do research to develop these things, some people are saying, do not reinvent the wheel. But if you don't have a wheel, what we should do? We have to reinvent. We have to start from the scratch. And when you do that, there are a lot of problems. But if you are in a difficult situation, like in what Dr. Lilantha mentioned, if you are in a difficult situation like Japan, how they developed after the bomb explosion. So if you are in a difficult situation, sometimes if you are in the correct path, you can boom. Now, you may have seen if you are pressurized, probably in these companies, those things are happened very well. If you are pressurized, sometimes you will do most of the important tasks. Like what thing happen in our cricket teams, if they are pressurized, they will perform. Likewise, from the school level, actually, if you can do something in this area, now we know IT is now there is a development and more people like IT literacy is improving. And likewise, in these kind of areas, robotics, we can use if you pressurize them and if you make aware from them from the school level. Now I think they have missed the bus. Unfortunately, they know they have awareness, but to create these kind of devices, we have to start from the school level, as we correctly mentioned. So in that case, there are opportunities in the elderly care also. In Japan also, there are a lot of elderly care robots, especially this kind of prosthetic and orthopedic device. Not only those, there are other kind of devices, chairs, and even the day-to-day activities. They are using robotic kind of devices in Sri Lankan context also. I think there are elderly care robots or devices we can develop.
Thanks. One more question to you, Dr. Ron. In terms of assistive robotics, we now have this a very interesting book, Rise of Robots, where they talk about the loss of jobs, the loss of blue collar workers' jobs.
Yes.
And this is particularly a problem, right? So, do you think assistive robots have or can play a role in making the employee more productive, right? So that they can still compete
with
the industrial robotics.
Industrial robots. So it's different actually. So there are places we can use assistive robots, and at the same time there are places we can use the industrial robots. Now, Dr. Leland get an example from the textile industry. So sometimes some industries they work in the standing positions, right? So long time standing position workers, also long time sitting position workers are there. So long time standing position workers, they felt some uncomfortable, and also they tend to have work-related disorders, back pains, kind of things. So these kind of situations, assistive robots or assistive devices we can use. So in those kind of situations, if you can use assistive robot or a device, so the person productivity improves. But if you consider industrial robots, those are working in environment isolated, in most cases isolated from the human beings, and they can generate more power and can do precise repetitions. Right? In those kind of areas, assistive robot cannot supersede the industrial robots. But if you need the robot need intelligence, dexterous motions in those kind of situations, assistive robot can supersede industrial robots.
Um, so, sorry. So this is a question to Dr. Lanka. In terms of the industrial robots, what are some of the typical processes, industrial processes that how do you identify an industrial process that is a good process for industrial robots?
It depends on certain parameters, like if the environment is harsh, where you cannot deploy people, and the degree of repetitiveness, the amount of accuracy you are expecting, the throughput that you are expecting, and whether you get trade unions or not. And a lot of parameters are there which is related to the product actually, the process that you are looking at. For example, if I take like automotive industry, if you go to Toyota Motor Company or Nissan, excuse me for